now going to be heading towards a very exciting chat between two of our leaders. First up, we're going to be having Alexi Ekimov, who's a Nobel Laureate 2023 chemistry, in conversation with Dr. Ramesh Bhargava, who's the Chairman and Chief Scientist Nanocrystal Magnetics, Inc. Allow me an opportunity to introduce both our speakers. Alexi is a Russian-American chemist who was awarded the Nobel Prize in Chemistry in 2023. He received the prestigious honor of the groundbreaking work in the development of quantum dots, which is nanoscale semiconductor particles that exhibit unique optical and electronic properties due to quantum mechanics. These discoveries have had a profound implication across various fields, including electronics, medicine, and display technology, amongst few. On the other side, we have Ramesh Bhargava, who is the Chairman and Chief Scientist at Nanocrystal Magnetics, Inc., which is a company known for its work in the world of nanotechnology, particularly in developing and producing advanced magnetic nanocrystals and materials. These nanocrystals have had implications and applications in various of the industries, including electronics, medicine, and energy. Under Mr. Bhargava's leadership, the company has made strides in advancing the use of nanotechnologies in emerging technologies such as magnetic resonance imaging, which is the MRI, data storage, and energy-efficient devices. Now it is time for me to cue in the console for playing the video on the screen and enlightening us with this wonderful chat on the other side. Over to the team.
Alex, welcome to PIWOT 2025. I think everyone here will be interested in your journey leading to the Nobel Prize for the discovery of quantum dots.
Thank you, Ramesh, and also I would like to thank the organizers, especially Red and Agrawal of Wheels, for the opportunity to address this meeting. Unfortunately, my health prevented me from attending this conference in person. Just a few words about myself. I graduated from school with a gold medal and continued my education in the physical faculty of St. Petersburg University. My scientific career started in the laboratory of Evgeny Fedorovich Gross at the JIO Physical Institute of the Academy of Sciences of the USSR. My research specialty was in the field of optical spectroscopy of semiconductors. Our work was motivated by the studies of optical pumping in gases of Arthur Kastler, who was awarded the Nobel Prize in 1966. In contrast to his research, we focused on the phenomena in semiconductors. For our work in optical pumping and spin polarized electrons in semiconductors, we were awarded by prestigious state prize of Academy of Science of the USSR. The next area of our research was concentrated and about quantum confinement of electronic excitations in semiconductors. The flurry of Nobel Prizes in the field of optics in semiconductors attracted us to study confinement in small nanocrystal particles of semiconductors grown in matters of glass, which were later termed quantum dots. This work was begun at JIO Institute and then continued at Vavilov State Optical Institute. The theory of phase decomposition of oversaturated solid solution helped us to develop technology to control size of the nanoparticles, starting from a few nanometers. This makes it possible for us to investigate quantum confinement in semiconductor nanocrystals. Our initial publication described these results, sparked an explosion in interest all over the world. This afforded me the opportunity to work in various institutions around the world like École Normale Polytechnique, Claude Bernard University, Lyon, France, Max Planck Institute, Germany, Sendai University and Osaka University, Japan. In 1999, I moved to the United States in the Laboratory of Nanocrystal Technology, headed by Ramesh Bhargava. Fundamental investigation for quantum confinement to electronic excitation in zero-dimensional quantum dots paved the way for commercial application of these nanomaterials in high-definition television and medical research using as biomarkers. Myself, along with Professor Bruce of Columbia University and Professor Moudji Bavendi of MIT, were recipients of the 2023 Nobel Prize in Chemistry for the discovery and synthesis of quantum dots. My colleague from Nanocrystal Magnetics, Dr. Ramesh Bhargava, will briefly present new findings and further development of these studies of these materials in the area of magnetism.
Well, with that, thank you so much, Alexi and Ramesh Bhargava. On that note, ladies and gentlemen, I'd also like to invite Mr. Ramesh Bhargava, who's amongst us right now, for his individual talk as well. His expertise is going to add a lot of value to PIWOT 2025. So with a mighty round of applause, let's call upon the Chairman and Chief Scientist Nanocrystal Magnetics, Inc., Mr. Ramesh Bhargava on the stage.
So let's begin where Alexi Ekimov's work won the Nobel Prize. That was the quantum dot, and it showed optical properties and certain applications. What we have done is extended that breakthrough discovery of quantum dots to the next level, where I'll just want to say it outright, that it may become the second electronic revolution of our times. This is for permanent magnets and all magnetic devices. Magnetic devices means anything moves will be using these type of magnets. Next slide. So Alexi Ekimov discovered the quantum dots. The applications were Q.TV and biomarkers, and they won the Nobel Prize in Chemistry in 2023. What we have done at Nanocrystal Magnetics is develop the doping of it. The doping concept is already known in semiconductors since the invention of transistor, because when you dope the transistor material like silicon, you can make p-n junction and transistor. But we use the doping concept, the discovery, to develop the spin control in nanoparticles. And the applications are strong permanent magnets used for electric vehicles, electromagnets, transformers, cell phones, drones, and the list goes on. The concept is very simple, but it only works in nanoparticles less than 15 nanometers. For the audience, a nanometer can be compared to, if you look at it, DNA diameter is 3.2 nanometers. We are working with particles which are 15 nanometers, 5 times bigger than the DNA diameter. If you take a nanoparticle and put an additional atom, which is shown as a sphere, if you decrease the size, that the sphere becomes oblong, and this change in the dimension of this atom, which is like a sponge, according to quantum mechanics, begins to polarize not only the spin, but also the optical properties. So everything depends on this quantum confinement, which Alexi also talked about. So this is the earlier result where we were able to put an atom inside a particle, nanoparticle, and not only we saw it's a very complex experiment, but the results were astounding because you can see the light coming from a single atom, which is asymmetry. It's not. It should be light going all direction, but we saw light is coming like a polarized light, similar to a laser. This gave us the impetus that this light is polarized and the magnetic field along with it must be polarized. So we started doing doping experiments on these small particles and realized not only we get the light polarized, but the spin of the system is polarized. And this is the beginning of so-called nanomagnetic systems. So let's just, for very simple reasons, compare the properties of electron used for semiconductor technology and what I'm predicting to be used for magnetic systems. Electron has only two properties, charge and its spin. When you control the charge and its flow, that leads to p-n junction and generates the so-called integrated circuits, and this is today is our life. Everything is using integrated circuits. If you take the second property, which is our discovery, is the spin, you can control the spin in 15 nanometer size particle by same technique at doping, and you can control the spin and you can make them ferromagnetic, which is really a magnet, or you can make nanowires, which are like a arrow of magnetic material, and these generate very large magnetic fields. And this integration of circuits, IC circuits we know today, is the revolutionary first electronic revolution. But if we integrate these nanowires and the nanomaterial, it is, I'll show you, can become the second electronic revolution. Now this is very complex data, but we have to show that we have 20 nanometer size particles and they align themselves with like an arrow and then can lead to the smallest magnet in the world. On the slide on the left is taken by so-called technique called atomic force microscope, where you can, with the tip of this, you can measure the size of the particles, and here they are 20 nanometers, and when they align themselves, you can make a 10 micron nanowires, which are, it's like you can take 500 of them and they make a very, very straightforward arrow. But when you combine these nanowires on the right side, you see we can demonstrate that is a magnet, and this is probably the smallest magnet we ever made. So this is the type of technique or the process of making it. We have been successful in demonstrating the magnetic property. Let's compare. There's a very fundamental problem today. There's a supply chain of rare earth materials coming from China. Rare earth magnets
permanent magnets are bread and butter for all electric vehicles and many other devices. China, due to its toxicity process, they control 92 to 95% of these materials. Everyone is looking to replace these rare earth magnets, and we have found a way to replace that, and let me compare the property. The rare earth magnets in China are basically made from neodymium iron boron system, which is called rare earth system, and the size of the particles they use is about micron, which is 1,000 nanometer, and we use about 20 nanometer size particle. So that's the size. The key thing is the fabrication temperature. They have to be fabricated at 1,000 degrees C or above, and in a very toxic condition, where we can do it below 100 degrees C, which is the boiling point of water. So it can be done in any controlled lab. The maximum operating temperature for these rare earth magnets is only 200 degrees. So if you have an electric vehicle and you live in Rajasthan, probably it may not work as well as in colder temperature. Our material can work up to 400 degrees C, and that it can be worked anywhere, and particularly for aerospace industry, this is very, very important. The process developed by Chinese is so toxic that 1 ton of rare earth material, they produce 2,000 tons of toxic waste, including radioactive material. So it's very difficult to dispose that toxic waste. There's an energy, the magnetic, or the magnets are compared with a scale they call energy product. The maximum value the rare earth can produce is 60, and for our material, the maximum is theoretically calculated to be 120, means 2x better than the Chinese rare earth permanent magnets. Now let's look at some of the novel applications which we can do from nanocomposites of these hard and soft nanoparticles which we are making. For electrical vehicles, we can have strong permanent magnets for all EVs, even better than what today we get it from China. But these permanent magnets would have a very large applications in defense industry, particularly if you're looking at drones, fighter planes, or anything which has a control with the magnetic interaction or motors, you have to use it. Now, renewable energy, people are using these magnets for wind turbines. But if you look at wind turbines, because they use rare earth magnets and in moisture and high temperature, they degrade. So a lot of wind turbines have a reliability issue. Here, because our material is already oxide, they're very, very reliable, and also they work at high temperature, so they would be much better for generation of electricity. Now in healthcare, I'll show you that we can make these nanoparticles and make an electromagnet far superior, which will allow us to make an MRI system which is portable. MRI system is very unique because it does not affect it's a sort of a radiation which does not affect the body. So people can do MRI, but also it is very good for cancer detection and other impairments. So an electric equipment like lightweight, smaller transformers, and efficient transmission, this is very important to today, if you have to have electric transmission systems in villages, this needs to be used. And the last thing is air conditioning, which we have the patent filing, but this is the solid state magnetic cooling for air conditioning and refrigeration. This was also mentioned by Ashok Jhunjhunwala yesterday. So just is a slide from Los Alamos and Naval Research Lab. If you look at just a transformer for high frequency, you can make 150 times as lighter and significantly smaller transformers, and transformers are the basis for all this power stations and transmission. So let's look at this application of magnet-based portable MRI. There's a company in New York which makes a stand-up MRI but does not use liquid helium temperatures for MRI detection. They use electromagnet, but it's huge system. What I'm saying that we are trying to work with them is if they use our powder, they can reduce the size 5 times and continue and make it almost portable, and that will change the whole MRI system of healthcare. It will be much cheaper, but eventually you can have MRI on wheels, which can detect cancer in any village. Those people don't have to find the MRI centers. So in summary, what we have achieved is a 15 nanometer size particle. Now, why 15 nanometers? It's somewhat a magic number because that's where the magnetic strengths, magnetic spins interact very well. So we are making permanent magnets from them, and beside Alex receiving 2023 Nobel Prize, we also received a key patent, US patent, on this non-rare earth permanent magnet system. And that competes directly with the Chinese permanent magnets. The composite powder we have made has advantage in creating enhanced performance in electromagnets, transformers, and particularly in magnetic cooling. Now, all these things, some of them, the products are already there, we are improving, but some of the next generation systems will be developed and can be developed in India. And when I say can be developed, it requires both scientific breakthroughs, but also manufacturing skills, and this is, in some sense, far superior to get into today, because in 5 years, India can lead this global industry, which could become as big as the integrated circuits technology. So if anyone wants to contact me, here's information, and I thank you for giving me the opportunity.
Thank you so much, Dr. Ramesh Bhargava, for joining us. Of course, we'd like to further invite on stage the co-chair of PIWOT 2023 and chairman Avalon Consulting. Ladies and gentlemen, let's give it up for Raj Nair. Apologies, co-chair PIWOT 2025, technical mistake. And of course, when we have such legendary figures, we've got Dr. Ramesh Bhargava, who's given such a fantastic address. His work has been exemplary in the field of nanotechnology. At PIWOT 2025, on behalf of Pan IIT, we'd like to humbly thank him. And we have on stage Mr. Raj Nair helping us with a felicitation. Thank you once again, gentlemen. Thank you for joining.